Hi everyone, welcome to another video of Intro to Machine Learning. In this video, we are shifting gears and we are not talking about a new model. Rather, we are talking about something known as dimensionality reduction, which is another important aspect of machine learning. In specific, I'll look at something known as principal component analysis or PCA. We'll try to understand the motivation and intuition behind it, and then also look at a Python implementation of this concept. However, I'd like to say that understanding the concept itself is more important than the Python implementation in this case. Okay, so what is dimensionality reduction? As the name itself reveals, it means we are trying to reduce the dimensions of the feature space, and that's what dimensionality reduction is. Let's say I have 100 features, right? And I'm trying to reduce it and bring it down to a smaller number so that it's easier to process. So why do we have this problem at all, right? An important aspect of large data sets is that we have these huge number of variables or features, right? And we need a way to deal with these features because the greater the number of features, the more computing resources we require, right? So as a result, we have certain techniques. There are certain ways of achieving this dimensionality reduction, and most of them can be categorized under these two categories. The first one is feature elimination. The second one is feature extraction. Okay, so what is feature elimination? Again, as the name itself suggests, this deals with reducing the feature space by eliminating features. Obviously, this has to be systematic, so there are many methods of doing it. So instead of considering every single variable, we can drop some of them, some of the variables that we feel are not having a greater impact on our outcome. And obviously, there are methods to deal with that. Okay, advantages of feature elimination methods include simplicity of modeling and maintaining a model such that we can interpret our variables, so we can understand our variables, right? One big disadvantage of eliminating features explicitly is that we might miss out on certain important aspects of the data set, right? So we might miss out on the information. Maybe that particular feature was important in a certain way, but we kind of eliminated that, right? So there is another dimensionality reduction technique that is different from feature elimination. This is known as feature extraction. And the principal component analysis that we are looking at today is a part of feature extraction. So what is this? Feature extraction is actually a larger term that's used for methods where we put together many features such that we can extract the most amount of information from them and then create some, maybe in certain situations, new features or new feature space so that we do not lose out on a lot of information, and still we create new variables that take into account the entire information that was depicted by the original variables. Okay, so the advantages of doing feature extraction as opposed to feature reduction is that we can reduce the number of resources, the computing resources that are required to process such huge information, right? And we can also reduce the amount of redundant data for a given analysis. And I would also add another point to it: we do not lose a lot of information, rather a lot of info. So we do not lose a lot of info in feature extraction. Okay, so going back to what I said, what we learn in this video is principal component analysis, which is a feature extraction technique that can be used for dimensionality reduction, as we shall see going forward. Okay, so what is this principal component analysis? Think of a two-dimensional feature space. Let's say this is x1 and this is x2. Let us assume that our data is distributed something like this, right? So we are trying to understand the way in any machine learning model, we are trying to understand the variability in data and how does that impact my outcome, right? Now you can see that there is a lot of variability across this direction, that's my x1, but there isn't a lot that's changing here, right, along x2. Which kind of tells me at a crude level, at a higher level, that maybe this x2 variable or x2 feature is not as important as x1, because x1 explains most of the variability in data, and that might help me more in predicting my outcome, right? So this is the first part or aspect of principal component analysis, that it's kind of dealing with some kind of variance in the data that tells me whether the outcome will be impacted by this particular feature or not. right? So this, just keep this in mind. Now, imagine that instead of 2 features, we have 3 features, 4 features, let's say 20 features. Are all of them important? Obviously, in most situations, the answer to that question is no. So what principal component analysis does is that it takes higher dimensional data, let's say more than 2, which is like 3, 4, 5, depending on whatever your data set is, and it flattens it so that we have fewer dimensions. So let's say if the original data set had 5 dimensions or 5 features, I can flatten it to 2 features, but I can, or I should be able to have it done in a meaningful way so that I preserve all the variance. This is important. I want to preserve the variance. I don't want to lose out on this variance, because this is going to tell me which maybe category a particular data point belongs to, or in case of regression, what is the outcome, and so on, right? So we want to preserve that variance. How do we do that? Again, a hypothetical example. Let's say this is x1 and this is x2, right? And let's assume I have like this much data only. Okay, right? Okay, so you can see just by looking at the way the data is distributed that I can capture the direction of most variation, right? Just by looking at it, I can tell somewhere here, this is the direction of most variation. This is the highest variability, right? So this is like the first uh, or the highest, you can say, variance, right? And then you can also see that the next variability is in this direction. If we are looking at only the orthogonal directions, right? We're not looking at any other direction but 90 degrees to one another, right? So this is the second highest variance direction, second most variation that happens, right? So if you look at these two aspects of variance, I can create my own x and y axis, just like I had here, right? This was the x axis, this is the y axis. How about I convert this into my x and y axis? In the in a way that this first or the most or the highest variance is something that I call principal component 1, and the second variance is principal component 2. If it had more features, I'll have one principal component for every feature. Now, I was just looking at a very simple case where I had only 2 features, right? So for every feature, I'm looking at where is that most variance, and I'm capturing them with these newly drawn arrows, right, or lines. With these are telling me the direction, and these and the length of the line is telling me the magnitude, right? So I can like take this, like pick these two up here and create my own x and y such that my x is PC1 now, because this is the highest most variance, and then the second most variance, maybe I can have the third most variance if, let's say, I had more features, right? So I was looking at 2 features only, so I created this new and then plot my data according to that. Right? So as I said, like if we had n features, I should have like n axes, and each of these is known as a principal component. So principal components are the directions of most variance where data is most spread out. So basically we are creating new dimension. So we are transforming our data into a new feature space based on variance, right? Now, another thing is that we want to ensure that all these principal components that we saw should be orthogonal, right? So they should be 90 degrees to one another. Why? Because we also want to have them as linearly independent, because those x and y axes are linearly independent. So we want to preserve that property, right? And then these should be ranked. So their length, as you can see, should be ranked according to the variance of data, because we just saw that PC1 is like seems at least longer than PC2, right? So we want to do something so that we can maintain all of these properties, the orthogonality, that's 90 degrees, the length, the direction, and everything, and then bring our data here or transform our data into this new feature space, and then make our predictions. So first of all, why is this important? This is important because each of my principal components will take care of most variation, and then I can get rid of some of these principal components, as we shall see. So we will reduce our higher dimensional data into a few dimensions of principal components and still preserve everything in my data and not lose out information. Okay, so how will I get these lines, right? How will I get the direction and these lines? So there is an algorithm for that. That's known as the principal component analysis algorithm, right? Step 1, normalize data, which means, let's say I have I'm starting with two features. Let's assume very simple case. By normalizing, I'll create new features, let's say x1, x2, such that both of them will have mean 0. Why do we need this? So that none of the features has a higher dominance over the other, right? So this is important, normalize the data so as to ensure that PCE works properly. So this is step 1. Step 2, we create the covariance matrix. If you've forgotten what a covariance matrix is, for any two variables, x1 and x2, this is a matrix of the covariance of, let's say, x1 and x1, which actually is nothing but variance of x1. Just like writing in brackets, covariance of x2, x1, covariance of x1, x2, covariance of x2, x2, which is again variance of x2. This is the covariance matrix. It is a measure of the joint variability of any two random variables. In our case, it's x1 and x2, which is our features, right? If the sign of the covariance matrix is positive, it tells us that the increase in one of the variables leads to an increase in the other. If they are negative, if the sign is negative, then it tells us that the increase in one variable causes a decrease in the other and vice versa. Right, so that's the positive and the negative sign of the covariance matrix. We can also look at the magnitude of the covariance matrix by calculating the correlation coefficient and finding out how large or small that the variance is. Okay, so we compute the covariance matrix because we want all the variance related information, right? Remember, we need variance related information, so that's why we compute the covariance matrix. Step 3, we find the eigenvectors and the eigenvalues. If you've forgotten, again, for any matrix A, let's say A is an n by n matrix, and there is a scalar lambda. So lambda will be the eigenvalue of A if there is a non-zero vector x bar such that this equation holds. Again, x bar is a vector and lambda is a scalar, and x bar here is the eigenvector of A and lambda is the eigenvalue of A. Now, why is this important here? This is important because the principal components that we talked about earlier, PC1 and PC2, they are eigenvalues and eigenvectors for our covariance matrix that we calculated in step 2. Right? So now all of that is making sense. Why do we need them? Obviously, we are trying to calculate the principal components, and those are our eigenvectors that will determine the direction of our new feature space, and the eigenvalues will determine their magnitude. Now the question arises how to find them. There is a known equation for that. So if lambda is an eigenvalue for the covariance matrix, and we can find the solution to this equation. I is the identity matrix and A is going to be the covariance matrix for any two features, right? So if you're able to find lambda here, right, then we should be able to solve this equation for every covariance matrix for a given vector x bar equals 0. What does this mean, this x bar? So we have to find this, and this is going to be our principal component, right? So we will find PC1, PC2 based on the covariance matrix of every two features, right? So if I'm talking about two-dimensional space, so it depends, right? I'm going to have a combination of more features if I'm looking at more principal components and so on, right? So it depends on like what feature space I'm looking at. Right now I'm looking at two-dimensional space, so A will be so we'll have like two principal components only because I'm going to have x1 and then x2. So essentially just think about like whatever the number of features we have, we will have a principal component for each one of them that will capture its variance. Okay, so how did it reduce my dimensions is the question that will come to you, right? Well, idea being that we will finally rank these, right? So we will order the eigenvalues from largest to smallest. Just remember, eigenvalue is going to tell me how long my line is going to be, that PC1 line, and eigenvector is going to give me which direction it's going to be, right? So we are going to rank them or order them so that it gives us the components in order of significance. And then depending on like whatever the domain of the problem is, we can decide how many principal components to keep. Right? So always remember it's up to us. It's up to us to decide how many eigenvalues we choose. So let's say we began with n variables, right? And k is some value that's less than n, and we think that the problem we're looking at should have k features. That's the max that we can keep. Let's keep that, right? We can also look at the actual principal component values like PC1, PC2, and see like if the magnitude is like really, really small, right? If one of them is like really small, we can eliminate it because it's not capturing enough variance in the data, and that is not really beneficial for our model. So that's why we can just eliminate them and then stick with one principal component that has the highest value, right? So this was step 4 and we are done. So essentially we'll have a new data set with new features in a new space. Now from here on we can apply whatever machine learning model we want to apply on it. Okay, so that's the Python implementation. Again, in the Python implementation, I'm looking mostly at the PCA part. I'm leaving the question of what model you want to apply on a certain problem open-ended, so that you should go and try once you have transformed your data. Okay, so this is the data set that I'm using. It's the red wine data set. It's available at this link. If you really want to visualize this principal component analysis and the transformation from one feature space to another, you should check the scikit-learn website for iris dataset. It's a very beautiful visualization that's given there. So let's look at our very simple kind of analysis. So let's keep this. This is the data that I have. Notice that I have a lot of features, right? Around 11 or 12 features. And what you're trying to predict is the quality. Now, again, it's up to you. How do you want to look at the quality? Maybe I'm looking at it as a categorical variable. Maybe it's not a categorical variable. Maybe it's a continuous variable. So I'm not going into the modeling part. I'm leaving that open-ended for you to try and decide. I'm looking at principal component analysis because I want to shrink these many features into just 2 principal components, maybe, or 3, right? So let's look at how we can do that. So again, I'm just importing a few libraries, reading the data set that I got from Kaggle, and feature scaling, as we said, normalization is important. Otherwise, one feature might have a domination over the other. So this is important. All these are a part of our earlier template that we've been using until now. And then I do a train test split here, right? Next, the important part is that there is this library called scikit-learn.decomposition from which we can import PCA. And I've decided to have 2 principal components or just 2 eigenvectors, right? So I've decided that this is an input parameter. You could decide for more. One important thing that I'd like to point out here is that once you've created an instance of your PCA, then you have to do a fit transform on the training data, but you don't have to do the fit transform on the test data. Remember, we have talked about it before, but I'm repeating it, that the test set is supposed to be having some new information, right? So that's why we just transform it. We do not fit anything to it. So that's the whole point. That's the basic thing here. And then here is the explained variance that we can, and there are a lot of other things that you can get from the PCA class. You should definitely go and explore that. So this is here, we'll create our new data in the new feature space. And now from here onwards, I'm going to work with these like for our modeling purposes. So essentially, I'll use xtrain and xtest for all my models. For example, I'm just showing you a very simple logistic regression model that I've implemented here to figure out the category of quality. However, you should like go ahead and try different models that we have looked at before. But the important thing that you have to remember is that we have to use this updated train and test. That's what's happening here. And then you can try getting your accuracy score and confusion matrix. So this is something that I'm leaving up to you to decide and go about with the principal components. Also play with the number of components and see how that affects your accuracy. I have also given a link to this code in the description box below. That's it for principal component analysis. See you in the next video. Thank you.